In this example, we will use the law of sines to solve the triangle if alpha equals 50 degrees, a is equal to 12, and b is equal to 14. We'll round to 2 decimal places. When the question asks us to solve the triangle, what that means is that it's asking to solve for all missing values. That would include any missing angle measures as well as any missing side lengths. In this case, we know A and alpha are always designated to be across from each other, and we know B. That means that we need to try to solve for beta. We need to try to solve for our third side length, C, and we need to try to solve for the other angle measure across from C, which is normally designated with gamma. We have 3 missing values we're going to solve here. Now the triangle that we have, if I make a quick sketch of this, 50 degrees would look something maybe like this. That is our value of alpha. We have a side length across from it that is 12. And we know another side length B, I can use either of the other missing side lengths to designate that. In this case, I'll choose to use this side length up here. And because I chose that one to be 14 or B, that means the angle measure across from it is now beta. And the other pair of values I have are C and gamma respectively. So that's a triangle that I'm working with here, and I'm trying to solve for the missing values. Now in order to do this, I should be able to apply the law of sines. The way that I know that I can use law of sines is because I have an angle measure as well as a side across from it. That is the bare minimum that you need to have in order to use law of sines. Since we have an angle measure and a side across, then we should be able to set up and use law of sines with one full ratio, in this case A and alpha, and then equal that to another partially completed ratio where we can solve for whatever is missing. For example, I should be able to use sine of alpha over A equals sine of beta over B, because I know what alpha is, I know what A is, and I know the side length of B. That means the only thing I'm missing is beta in that equation, and I should be able to solve for that one missing variable. So that's what I'm going to use here. If I set that up over on the left side, this will look like sine of alpha is 50 degrees divided by its a side length that is across from it, which is 12, equals sine of the angle measure I want to try to solve for is beta over the side length across from it, which is 14. I cannot currently use law of sines with C and gamma because I don't know either part of that ratio, but I soon will. For now though, with sine of beta over 14 and sine of 50 over 12, I should be able to solve for beta by multiplying both sides by 14. To get sine of beta. And then I can take arc sine of both sides in order to approximate beta. Beta would be arc sine of 14 sine of 50 degrees over 12. All right. Now, at this point, I should use a calculator to solve this. However, note that the answer that we expect for this, I would expect an angle measure larger than 50 degrees. The reason why I know that is because the larger the angle measure, the larger the space it opens up. I know A of 12 is across from an angle measure of 50 degrees. My side length of 14 for B should likewise, since that is a larger side length, be across from a larger angle measure as well. So, since B is a larger side length, it should also be across from a larger angle measure. But at this point, let us use a calculator to approximate this. Do make sure that you are in the correct mode, in this case degree mode since we're using 50 degrees. But I will use inverse sine of 14 sine of 50 degrees divided by 12. And that gives me about 63.34 degrees, which is about what I expected since it is larger than 50 degrees. So 63.34 to 2 decimal places. Since I now have beta, I now should be able to solve for gamma, and I can do that without the law of sines because I now know 2 angle measures in this triangle. I know alpha and I know beta. So, since the entire 2-dimensional triangle should have 180 degrees, I can subtract those 2 values of 63.34 and 50 degrees. If I do that, 180 minus 63.34 minus 50 gives me 66.66 degrees. So now we have beta and gamma. The only missing piece left is C. But as I said, since we know gamma, now we should be able to set up a ratio involving C and gamma. Now we can set sine of gamma over C equal to any of these ratios now. It doesn't have to be beta over B, doesn't have to be alpha over A. However, I'm going to choose to set sine of gamma over C to be equal to sine of alpha over A. The reason for that is because sine of alpha over A uses 2 values that I was provided. If I set it up equal to sine of beta over B, then I'm setting it equal to a ratio where I only had one of those values provided, and the other came from a calculation. So I like to set it up equal to sine of alpha over A in this case, because I'm using values that I was provided to know to be true. So then, if I want, in this case, C, what I'm going to do is structure this ratio so that the side lengths are on top. So I will say C over sine of the angle measure across from C is gamma, which I now know is 66.66 degrees, is equal to, if I structured side lengths to be on top, that should be true for all ratios. I'll set that up equal to, in this case, 12 side length for A over sine of the angle measure across from A. If I solve for C there, that now means that 12 times sine of 66.66 degrees divided by sine of 50 degrees will allow me to approximate and solve for C. Again, let's use a calculator for that purpose. Do make sure that you are in degree mode, however. So that will be 12 sine of 66.66, and I will divide that by sine of 50 degrees. This gives me 14.38, which that side length makes sense to me because my largest angle measure ended up being gamma in this case. That therefore means it should likewise be across from the largest side length. So 14.38. So, we now have values for beta, gamma, as well as C, and therefore have solved the triangle. However, I am not technically done at this point. The reason for this is because this is one of the triangles that we need to be careful of, based on the information that was provided to me at the beginning. Since I was provided an angle measure, a side length, and a side length, this is what we would call a SSA triangle. And in SSA triangles, we need to be worried about what are called ambiguous cases. The ambiguity of SSA triangles comes from the fact that the first thing that you need to solve for forces you, we look down here, the first thing that we solved for forced us to use an inverse trig function, specifically arcsine. The reason that is a problem is because arcsine would not be able to produce an obtuse angle measure even if the answer should be obtuse. It can only give us an angle measure between technically negative 90 degrees and 90 degrees, or for realistic triangles, 0 to 90 degrees. So we need to accommodate for the fact that we're using arcsine here. What we need to do is also consider another version of this triangle. Essentially, the picture of this triangle that would have a side length of 14 and 50 degrees. That 12, instead of going off to the right like I currently had it drawn, we're basically going to consider this instead with having 12 coming down at more of a sharp angle measure. That would still have 50 degrees, 14, and 12, but now the angle measures that we're going to solve for are going to be different. And the one that we're going to calculate down in the corner, down here for beta, is technically going to be the supplement of what we had calculated before. That is how we're going to calculate the second set of solutions, if there exists one, for SSA triangles. You can also compare this to when we had talked about inverse trig functions, where you would have one solution that would be arcsine of whatever you're working with, and another solution that would be pi minus arcsine of whatever you're working with. Or, in degree measures in this case, 180 degrees minus. That's what we're going to apply here. In this case, because this is the secondary set of solutions, I'm going to differentiate them with primes. So I'll say beta prime, gamma prime, and C prime. For example, here, beta prime, I will say instead of 63.34, I'm going to take 180 degrees and subtract the solution that I had calculated before. So I'm going to subtract beta. That will be 180 degrees minus 63.34. If you do that, that will give you 116, 0.66 degrees. That would be the value of beta prime. Another solution for beta. At this point then, solve just like we did before. If I want to find the third angle measure, in this case gamma prime, just like before, take 180 minus the two angle measures I know. In this case, instead of 63.34, I'll subtract 116.66 degrees and 50 degrees. I still know that alpha is 50 degrees. And what that is going to give me is 13.34 degrees. Now, it is called an ambiguous case because you do not necessarily know at the beginning if you're going to have multiple solutions. Sometimes you'll only ever have one. And at this point, you should know whether you only have one or two or maybe no solutions. If we try to solve for this third angle measure and the angle measure doesn't make sense in a realistic scenario, For example, if this came out to be a negative angle measure, well, that wouldn't make sense. Therefore, then we would not have a secondary solution for this case. You may also have situations that give you context that tell you that we're working with an obtuse angle measure or imply that, or maybe we're working with an acute angle measure and imply that. And we would only have one set of solutions instead of possibly two. But for this scenario where we don't have much context, if we solve for a third angle measure and it's negative, then we are not going to have a secondary set of solutions. At this point, though, we can solve for C. We're going to solve for C again in the same way. However, in this case, it's technically C prime. This would be over sine of the angle measure across from C prime would be gamma prime, which is 13.34. That is still equal to, I'll set it equal to 12 over sine of 50. Which means C prime will be, if I multiply sine of 13.3 over 12 sine of 13.34 degrees over sine of 50 degrees. Which, if I approximate, I expect a very small angle measure, or side length, because it's across from the smallest angle measure. Again, keep in mind we're still in degree mode here. 12 sine of 13.34 divided by sine of 50. That gives us a very small side length of 3.61 approximately. So we have now solved for this triangle for both possibilities. Keep in mind again, we had multiple possibilities because we were working with a side-side angle triangle. If we were working with another type of triangle, for example, an angle-side angle triangle, we would not have to worry about this. And that is mainly because that kind of problem would not force us to work with arcsine first in order to evaluate our first missing value.